Oh, hi! Didn't see you there. Just grabbing some baking soda. And I love baking soda. It has so many wonderful uses. You can cook with it, you can clean with it, you can even get rid of bad smells. And I've heard there's a couple uses in the bathroom. Have you ever wondered what the statistical equivalent of baking soda is? I know you have. Multiple regression. Multiple regression. Multiple regression. Okay. All right, moving on. Welcome back to another episode of Statistical Know-How with me, your host, Dustin A. Fife. And today we have a very special guest by the name of Dr. Poche. Dr. Poche, why don't you introduce yourself?
My name is Dr. Paul Poche, and I am an expert in quantitative psychology.
Thank you, Dr. Poche. So first we're going to talk about what is regression. What is it actually doing? And so the best way that I know of to actually understand what regression is doing is to look at a scatter plot. So let's go ahead and look at a scatter plot. All right. So in the top graphic, we see a model that is not fitting very well. The lines do not go through the data point. That's exactly what regression is trying to do. It's got all these data points, trying to fit them, trying to find a line that goes right through the densest part. And the bottom one, doing pretty good, isn't it? All right, so like I said earlier, or that other guy said earlier, regression is really the big daddy of statistics, right? We could do like anything in it. We could do ANOVA, we could do t-test, we could do structural equation modeling, we could do logistic regression if we modify some things. We could do a z-test, we can do a related to t-test, we can do it all. Basically, regression is awesome. It is the baking soda equivalent of statistics. How amazing is that? So it is super duper duper flexible, but it has its limitations. And to introduce those limitations, please welcome Dr. Poche.
Yes, regression has limitations. If you will look at the next slide, you will see two models, Model 1 and Model 2. Model 1 is predicting anxiety from depression, while Model 2 is predicting anxiety from depression as well as stress. So if you were to look at the parameters of the model, the coefficients in Model 1, we have 0.8 multiplied by depression, suggesting that for every increase in depression, we expect anxiety to increase by approximately 0.8. Whereas in the second model, we have a coefficient of 0.5, suggesting that the two models give different theoretical results. So, what does this tell us? We tell us that there is a problem with regression. That when you have two or more predictors, we run across a problem called multicollinearity, or just collinearity for short, which means that two or more predictors are correlated with one another. That's all it means.
All right, good. Thank you for that rousing explanation of collinearity. So, why is collinearity a problem? Well, it's really a problem for two reasons. One, we have a hard time identifying which predictor gets credit. Okay? So, if two variables are correlated and they share information in predicting the outcome variable, well, who do you give credit to? Okay, that's one problem. And the second problem, probably a bigger problem, maybe not, depending on your perspective, is the standard errors increase. So you have a lot more variability in the prediction of what the slope is going to be.
But of course, it can. But of course, it can get much worse. Suppose we have two models. One where anxiety and depression are. Where anxiety is predicted from depression. And another model where anxiety is predicted from depression, mother's depression, father's depression, mother's anxiety, father's anxiety and stress. And so in the first model, we see that the depression is an important predictor in the model, 0.8 coefficient, and in the second model, it is only 0.001. And so in the second model, it seems to indicate that depression is not an important predictor in the model. There.
So which is it? Is depression important? Is it not important? It's kind of hard to tell from this, isn't it? But here's the bigger problem that I have. It just seems wrong, right? The theoretical interpretation of the model depends on what other variables are in the model. Doesn't that seem kind of wrong to you? Seems wrong to me. But that's just a fact of regression. It's super sensitive to what other variables are in the model. Darn. So you might be asking yourself, okay, so how do I tell if multicollinearity is a problem? Well, simple answer. If you're using regression, multicollinearity is a problem. It's going to be there. Now they all have these statistics like the variable inflation factor that give you some kind of guidelines like if VIF is greater than 10, time to freak out. But really, I never look at them honestly. Okay, I think there's other strategies we can use to deal with the multicollinearity issue. Right, Dr. Poche?
Yes, that is correct. Yep.
So in regression, we have 3 goals that I'm going to talk about. And those goals are number 1, prediction. Number 2, exploration. And number 3, explanation. And regression can do all 3. And the strategies you use are going to depend on what your goal is. So let's first talk about explanation. So if we're trying to explain something, we're trying to determine some sort of causal relationship. What is going on? What is causing this variable to behave this way? And in situations like that, again, the problem is going to be assigning credit. So how do you assign credit? Well, standard regression, nobody gets credit. It's like a pissed off parent when kids are fighting over toys, you know? Nobody gets the toy! Well, that's what regression says. Y'all gonna fight over the credit? Well, nobody gets credit. So in regression, you only get credit for your unique contribution. If you don't share any information with anybody else, that's where you get credit. So the best way that I've found to deal with this issue of multicollinearity is by having theory to back your analysis. That's really the best way of doing it. And there's really 2 ways we can do that. Number one is we do targeted hypotheses. It's kind of what I talked about last time, where you have a very strong theoretical reason for predicting something. That's what a targeted hypothesis is. So you can ask yourself, what is my question? And then once you understand what your question is, then you can translate that into statistical language and statistical modeling. That's the basic idea behind it. The other way isn't all that different. It's through what we call model comparisons. So model comparisons, you've got 2 competing theories for the data, and you pit them against one another and see who comes out on top. So back to this idea of a targeted hypothesis. You remember when we talked about crafting good hypotheses? So let's think about a regression model where you've got, let's say, 3 predictors, x1, x2, x3. How many hypotheses can you test there? Well, you got the main effect of x1, the main effect of x2, the main effect of x3. You got the interaction between x1 and x2, interaction between x2 and x3, and the interaction between x1 and x3. And then you got the three-way interaction. So that was 4 here and then 3 here. We got 3 hypotheses we could test. That's not even including the intercept. If you include the intercept, that's 9 hypotheses we can test. And we've got the potential for polynomial terms. That's a whole lot of hypotheses to test. So what we talked about last time is having targeted hypotheses and identifying the specific parameters that you're interested in. Oh, by the way, that's not even counting all these sub-models you could have, like you could decide to control for x1 and x2 but not x3, and you could have different subsets of the models. You could have two-way interactions but not three-way interactions, two-way interactions between these variables, not these variables. There's lots and lots of variables you could test here. And that's a problem unless you have a targeted hypothesis, a specific parameter that you are interested in your analysis. And by the way, let me get on my soapbox for a minute here. You ever seen tables like this? Yeah, we see them all the time. Like, really? What's the point? Are you really testing 100 hypotheses here? Come on, people! Every one of those hypotheses is like rolling the dice. Okay? If you roll the dice 100 times, you're going to get a rare event every once in a while. So these, they don't make sense to me. So if we're doing null hypothesis significance testing, really we only get one shot. What is your one parameter that you want to test? And sometimes you want to test more than one, and that's okay, provided that you adjust for multiple comparisons when you do that.
So in a regression model, it is important to talk about the statistics of interest for your model. It really depends on what your targeted hypothesis is, as Professor Fife mentioned previously. So, are you interested in the parameter, or I'm sorry, the interaction, the main effect, or the partial effect? Either way, the statistic of interest is going to be one of two things. It is either going to be the parameter itself, such as the slope or the partial slope, or the interaction term, or the mean difference, or it's going to be the standardized parameter, such as a semi-partial r-squared, or a standardized beta, or a Cohen's d, or some sort of procedure such as that. Are there any questions?
They can't hear you.
Oh, yeah, right. Okay. My apologies. Oh, as they say, if you have any questions, you can write them in the comments below, and otherwise we can talk about them in class. So as another quick side note, people often ask, what is the minimum sample size required when doing a multiple regression analysis? And the question that I often ask is minimum for what? You know, what are you trying to accomplish? And so typically the standard way to approach this is that you operationalize it as the minimal sample size required to obtain power of 80% or greater, which is a standard null hypothesis significance testing approach to determining the sample size. So I find it much more efficacious to operationalize based on the size of the confidence interval you wish to have. And that will depend on the number of predictors in the model, and as well as the size of the effect that you're predicting will happen. And again, this too requires very careful targeted hypotheses, and the power calculations themselves are actually about specific parameters.
And that's actually a very good point, because often people will ask me to do a power calculation. I say, okay, what kind of analysis are you doing? And they say, we're looking at the relationship between depression and anxiety, stress, mother's stress, father's stress, father's IQ, mother's shoe size, and waist circumference. And my follow-up question is always, all right, which parameter in that model are you interested in? And most people have no idea what I'm talking about. And that's not how a power calculation works, people. You got to tie it to a specific parameter.
Yes, exactly. Thank you, Professor. Okay, so a model comparison, that's a very important principle in there. Okay. It's a very important principle in statistics, and a model comparison is nothing more than just a special form of a targeted hypothesis. They overcome the limitations of regression in the exact same way targeted hypotheses do. And that is with theory, with statistics backed with theory and with a specific hypothesis in mind. But there are two types of model comparisons. One is a nested, and the other is a non-nested model comparison. So how you can tell whether let's see, I got out of the camera there we go. How's that? Yeah. Can you all see me? Oh, that's right. You can't talk to me. Okay. So with a nested model comparison, you have you can always identify whether it's a nested model if you can delete one part of the model to obtain the other model. So for example, if you have a model where y is equal to a plus b, for example, and in model 2 it is y equals a plus b plus c. Well, if you simply delete model c, variable c from the second model, you obtain the first model, and that's what a nested model is. And what we learn is that when oh dear, I'm getting ahead of myself here. I'm sorry. Oh, maybe I'm not. Let's see here. Oh, yeah. Now mathematically, I get that there's a lot of confusion about this, that a model comparison is mathematically identical to covariating out the other variables. So for example, if you have a model with A, B, and C, and you compare it to a model with A and B, what you are doing is in the second model, A, B, and C, you're simply just covariating out the effects of A and B and identifying what the unique contribution of variable C is. And so often I will have people come to me and they do as they say in SPSS, it's a hierarchical model where they have model A and B in the input there, and then they have a second input in the hierarchical regression where it's model A, B, and C. And I tell them that's entirely unnecessary, because in the second model you're really only asking about the unique contribution of C. But if you were to run just the model with A, B, and C and look at the coefficients and the parameters in the model, the C there will give you an identical result as if you did a hierarchical regression. Because a model where you run A, B, and C, remember that the effect of C is controlling for the effects of A and B. And if you were to do a hierarchical regression, you're telling the computer to control for the variables A and B and then add the third variable in, so it don't make one bit of difference either way. It's the same thing. If you're in both models, you're controlling for A and B, and it's mathematically identical.
So basically, there's really no difference between a covariate adjustment and a model comparison. Or is there? Well, actually there is. There's a psychological difference. So with the first type, where you're doing a covariate adjustment, what you're basically saying is, I don't care about variables A and B. I want to get rid of them. They're not of interest to me. And so that's how you typically think of a covariate adjustment. You're getting rid of those variables. You don't care about them. Whereas with a model comparison, it's a different psychological interpretation. You're saying, all right, we already know that A and B are important. Now, what happens when I add C? And so it's a slightly different psychological interpretation, but that psychological interpretation is important because it steps us away from this standard way of doing a null hypothesis test, where we are comparing our model to a model where nothing's going on. Well, that's not a very interesting model. But what it is an interesting model is you have this existing model of reality and you want to identify whether adding this new model improves above and beyond what we already know. That's a cool question to ask.
Yeah, that's correct. And so we talked about a nested model, and there are also non-nested models. The advantage of nested models is they're very easy to compare, and the reason why is because since one model is simply a subset of another, and we know that when you add a predictor, it's impossible for the fit to get worse. And so, given that you know that the model will improve, it's just a matter of simply comparing and seeing, all right, if I add another parameter or another variable to this model, does it improve the fit enough to justify its inclusion? Whereas with non-nested models, they're not so easy to compare because there is no theory suggesting that one model will always be better than another, and there's no theory suggesting how much of an improvement is enough, because again, there's no guarantee that non-nested models that one will not be better than the other. So yeah, there's that point. So like an example of a non-nested model would be model 1 is variable y is equal to a plus b, and model 2 is equal to y is equal to c plus d. And you can't cross out any terms in one model to get the other. So there are some tools we can use. We can't use the standard tools that we use in regression, like the F ratio or test of statistical significance, really. Instead, there are other tools we could use. We could use the AIC, which stands for the Aka-Icki's information criteria. I've always enjoyed saying that word. That's just a fun word to say. Aka-Icki. Yeah, I like that word. Yeah. And then the other one is the Bayesian information criteria, the BIC. And so what we can do is we can compare the AIC and the BIC, which again, they're just numbers. Don't trouble yourself over how they're computed or how they came to be. Just know that they are statistics that we can use to compare two models that are not nested. And so if you ever take a test or something and they say, what's the purpose of the AIC or the BIC, you might... Can you hear me now? Okay. Well, we'll just record that one over, I guess. Yeah. Okay. Let's see. Where was I? Let's see. Oh, okay. So we've had an unfortunate string of technical difficulties. So the camera cut off, and I forgot to turn on the microphone, and I probably spoke here for 3 or 4 days or so, and I didn't notice that the microphone wasn't on yet, so I'm gonna have to record all that again. Oh, no, that's not necessary. Why don't you just quickly summarize AIC, BIC, and then we'll be good. Oh yeah, absolutely. Okay, yeah, I can do that. So the AIC and the BIC, as I said, they're two different measures that are designed to measure non-nested models. And the rule of thumb is that whatever model has the smaller value of the AIC or the BIC, that is the model to be preferred, to be chosen. They say that's the better fitting model, and we ought to choose the model with the smaller AIC or BIC. Now, one thing it does not answer is now I'm all nervous. I don't know if we're recording. Are we recording now? I mean, I see a red light. I think red light means go, right? That's kind of funny that, when you go to a stoplight, that green means go, but on a camera, red means go. I find that humorous. It's funny. Oh yeah, that's right. I gotta stay on track here. So yeah, so the AIC and BIC tell you which model, but they don't tell you by how much better it is. And so I've had some. Oh, excuse me, it's getting late here. Yeah, so I've had some ideas here and there about maybe bootstrapping the estimate and identifying a distribution. It seems an obvious approach, and I'm sure somebody's done it before, but I never have read any literature that actually does that. So, maybe if you have an interest in writing a paper, and if it hasn't been done, I'd be certainly willing to collaborate on that. So yeah, I think that's all I have to say.
Excellent, thank you. So just in summary, we got to one of the three goals in regression. We talked about explanation. Next time we're going to talk about prediction and exploration. Well, before we talk about that, we're going to talk about graphics and how to visualize multiple regression, including the amazing and powerful tool called FlexPlot. And we also talked about how regression is the big daddy of statistics. It's really the thing that does it all. Just about every statistical procedure you see is a special case of regression, which is awesome. We also talked about conditioning and how regression struggles to identify who gets credit, and so it just defaults to giving nobody credit. And so variables that are important are ones that offer unique information in predicting the dependent variable. We also talked about two reasons multicollinearity is a problem. It increases the standard errors and it makes the theoretical interpretation of the model questionable. And so how do you combat that? Well, the best way to do that is through theory-driven hypotheses, that you specify in advance what your hypothesis is through a targeted hypothesis or through a model comparison. And just make sure you understand the difference between the psychological difference between a covariate adjustment and a model comparison, and how that fits into null hypothesis significance testing. So, peace out, my statistical Padawans. It has been a pleasure. And Dr. Poche, we really appreciate your expertise and your guidance and your excellent teaching demonstration and your grasp of the knowledge. We are eternally indebted to you for your wisdom, your patience, and your insight.
Very kind of you to say. Thank you very much. It's been a pleasure. Goodbye. Is that what I say? Oh, okay. Well, goodbye. Have a good day now. It's been nice talking to you, and I hope you're safe, and that the weather near you is comfortable and to your liking. And I do wish you the best in all your statistical endeavors, or otherwise for that matter. Maybe you're just passing along and don't even have an interest in statistics, which is fine. Albeit unfortunate. I think everybody needs to have an understanding in statistics, and and it certainly makes you a better informed person, and able to read the news with an eye of skepticism, and really it brings a sense of happiness and peace and satisfaction. You know, some people meditate, some people do statistics, and I'm part of the latter group.
I couldn't give a straight face for that one.